Okay, recording. Reading. This is a recording for Math 120, Session 1. Especially I'm recording this for the online students, but on-campus student also, you can use this later on to help you with the lesson and the topics that we study in the class later on at your home. You can use this recording too. Let's start with prayer. Father God, we thank you for this time. Thank you that we can learn about the subject of mathematics, which is a reflection of your great, infinite wisdom and knowledge, and help us to understand how you have created this world. At least it helps us to understand in a limited way, with our limited mind, the great pattern, your great knowledge, your great power that you have used to create this world, because we can see a mathematical pattern in the creation. We commit this time to your hand, we commit this session into your hand, and this whole course into your hand. May it be a time that we grow not only academically, not only we learn about mathematics, but also we gain a deeper appreciation for you, O Lord God, for your knowledge and wisdom. And may it be that we can use the tools that we learn in this class in our own lives and in our ministry, in church, or different kind of ministry that you have given us. We commit this session into your hand. I ask your blessing upon all these dear students. We pray all these things in Jesus' mighty name. Amen. Let's start with the PowerPoint, and let me go to the shared PowerPoint right now, the share screen. Okay. Session 1, I know lots of you guys have told me already that you have fear and anxiety about mathematics, but I want to assure you there's nothing to be afraid of. Mathematics is a very logical, very organized science that if you learn the basic foundation, it can be very easy. In fact, in my undergraduate degrees, one of my major was mathematics, the other one was physics, and the reason I chose mathematics was provided if I understood the main principle, provided that I understood the principle and foundation of mathematics, then there was very little work to do. Everything else would follow a very logical pattern. So don't be afraid. And also, if there's any question, anything that you don't know, please don't hesitate to contact me. Even for the online student, please contact me, send me your question. I will either respond to you with the email, or I can also record a special section, a special segment to respond to your question. Okay, so don't be afraid. You will enjoy mathematics, but please just keep going with all the lessons that we have, all the homework and assignment that you have for every week. One of the things that I want to ask you for this class, please don't use calculator. We want to develop and grow in our own mathematical skills, in our own mind. Please don't use calculator, at least for this class. You can use it for later on, but not here in this class. The next slide tells you something about me, about who I am. I was born and raised in Iran in a Muslim family. I was practicing Muslim. I came to the saving knowledge of our Lord and Savior in the year 1981, and I'm involved in the following ministry: pastoring Iranian Christian Church of El Cajon, pastoring Iranian Christian Church of San Diego. I'm a professor at Southern California Seminary, and I have a TV and radio program via satellite to Iran and Afghanistan. and praise the Lord for the work that the Lord is doing in those countries. I received my doctorate degree last May 2018 from Southern California Seminary. I also have a THM degree from Southern California Seminary, Master of Divinity, MD from Trinity Evangelical Divinity School in Deerfield, Illinois, near Chicago. Got my Bachelor of Physics at Point Loma University and Bachelor of Mathematics at the same university, Point Loma. Here's my email, and you have my cell phone number. Contact me for any question that you have. In mathematics, you will learn many glossary and symbol. Mathematics is like a language, so you need to know the vocabulary of this language. So you need to know the glossary and symbols. But once you understand, once you memorize few things, other ones, the rest of it follows a very logical pattern. And there's, again, provided that you understand the principle, it's very easy. And there's, in comparison to other courses, there's much less work to do. One thing about a limitation that we have for online student or even on-campus student, because we are using Populi, the school changed from Blackboard to Populi. Populi has some limitation in using math symbols. But I put here these two websites that you can copy and paste math symbols which are compatible with Populi. Some things that we can even using with these two websites, and that's why I had to just ask you to download, then either type or write with your hand, and then scan and upload your assignment. Unfortunately, that's a limitation of Populi. That comprehensive general math test that I asked you to do, please do that before the beginning of the week number 1. And that's only an extra credit, so you don't need to worry about it. It's just an extra credit that will help you, and it helps me to assess your level of mathematical understanding. So don't sweat about it, just do your best and don't worry. We will work those topics throughout this course. So, that question here, finding x, actually has to do with the Pythagorean theorem that we can watch that on a YouTube. In fact, why don't we do that? Let me copy this and go to YouTube, and we can watch this together. One moment.
This video, we're going to get introduced.
All right, let me just put that. Okay, let's go here.
In this video, we're going to get introduced to the Pythagorean theorem. Pythagorean theorem, which is fun. It's one of those cornerstone theorems of really all of math. It's useful in geometry. It's kind of the backbone of trigonometry. You're also going to use it to calculate distances between points. So it's a good thing to really make sure we know well. So enough talk on my end. Let me tell you what the Pythagorean theorem is. So if we have a triangle, and the triangle has to be a right triangle, So it has to be a right triangle, which means that one of the three angles in the triangle have to be 90 degrees. And you specify that it's 90 degrees by drawing that little box right there. So that right there is, let me do this in a different color. That right there is a 90 degree angle, or we could call it a right angle. And a triangle that has a right angle in it is called a right triangle. So this is called a right triangle. Now, with the Pythagorean theorem, if we know two sides of a right triangle, we can always figure out the third side. And before I show you how to do that, let me give you one more piece of terminology. The longest side of a Pythagorean, of a right triangle, is the side opposite the 90-degree angle, or opposite the right angle. So in this case, it is this side right here. This is the longest side. The way to figure out where that right triangle is, and it opens into that longest side. That longest side is called the hypotenuse. Hypotenuse. And it's good to know because we'll keep referring to it. And I just so we always are good at identifying the hypotenuse, let me draw a couple of more right triangles. So let's say I have a triangle that looks like that. A triangle that looks, let me draw it a little bit nicer. So let's say I have a triangle that looks like that. And I were to tell you that this angle right here is 90 degrees. In this situation, this is the hypotenuse because it is opposite the 90-degree angle. It is the longest side. Let me do one more just so that we're good at recognizing the hypotenuse. So let's say that that is my triangle, and this is the 90-degree angle right there. And I think you know how to do this already. You go right, what it opens into, that is the hypotenuse. That is the longest side. The longest side. So that is the hypotenuse. So once you have identified the hypotenuse, and let's say that that has length c, and now we're going to learn what the Pythagorean theorem tells us. So let's say that c is equal to the length of the hypotenuse. So let's call this c. That side is c. Let's call this side right over here. Let's call this side right over here a. And let's call this side over here b. So the Pythagorean theorem tells us that a squared, so one of the shorter sides, the length of one of the shorter sides squared, plus the length of the other shorter side squared, is going to be equal to the length of the hypotenuse squared. Now, let's do that with an actual problem, and you'll see that it's actually not so bad. So let's say that I have a triangle that looks like this. Let me draw it. Let's say that this is my triangle. Looks something like this. And let's say that they tell us that this is the right angle, that this length right here, let me do this in different colors, this length right here is 3, and that this length right here is 4. And they want us to figure out that length right there. Now, the first thing you want to do before you even apply the Pythagorean theorem is to make sure you have your hypotenuse straight. You make sure you know what you're solving for. And in this circumstance, we're solving for the hypotenuse. And we know that because this side over here, it is the side opposite the right angle. If we look at the Pythagorean theorem, this is C. This is the longest side. So now we're ready to apply. We're ready to apply the Pythagorean theorem. It tells us that 4 squared, one of the shorter sides, plus 3 squared, the square of another of the shorter sides is going to be equal to this longer side squared. The hypotenuse squared is going to be equal to c squared. And then you just solve for c. So 4 squared is the same thing as 4 times 4. That is 16. And 3 squared is the same thing as 3 times 3. So that is 9. And that is going to be equal to c squared. Now, what is 16 plus 9? It's 25. So 25 is equal to c squared. And we can take the positive square root of both sides. C, I guess, just if you look at it mathematically, could be negative 5 as well. But we're dealing with distances, so we only care about the positive roots. So you take the principal root of both sides, and you get 5 is equal to C, or the length of the longest side is equal to 5. Now, you could use a Pythagorean theorem if we give you two of the sides to figure out the third side, no matter what the third side is. So let's do another one right over here. Let's say that our triangle looks like, something like, this, and that is our right angle. Let's say that this side over here has length 12, and let's say that this side over here has length 6, and we want to figure out this length right over there. Now, like I said, the first thing you want to do is identify the hypotenuse, and that's going to be the side opposite the right angle. We have the right angle here, you go opposite the right angle. The longest side, the hypotenuse, is right there. So if we think about the Pythagorean theorem, that a squared plus b squared is equal to c squared, 12 you could view as c. This is the hypotenuse. The c squared is the hypotenuse squared. So you can say 12 is equal to c. And then we can say at these sides, it doesn't matter whether you call one of them a or one of them b. So let's just call this side right here, let's say a is equal to 6, and then we say b, this colored b, is equal to question mark. And now we can apply the Pythagorean theorem. A squared, which is 6 squared, plus the unknown b squared, plus b squared, is equal to the hypotenuse squared, is equal to c squared, is equal to 12 squared. And now we can solve for b. And notice the difference here. Now we're not solving for the hypotenuse. We're solving for one of the shorter sides. In the last example, we solved for the hypotenuse. We solved for c. That's why it's always important to recognize that the a squared plus b squared plus c squared, c is the length of the hypotenuse. Let's just solve for b here. So we get 6 squared is 36 plus b squared is equal to 12 squared, that's 12 times 12, is 144. Now we can subtract 36 from both sides of this equation. Subtract 36, those cancel out. On the left-hand side, we're left with just a b squared is equal to, now 144 minus 36 is what? That is 144 minus 30 is 114, and then you might subtract 6 is 108. So this is going to be 108. So that's what b squared is. And now we want to take the principal root, or the positive root, of both sides. And you get b is equal to the square root, the principal root of 108. Now let's see if we can simplify this a little bit. The square root of 108. And what we can do is we can take the prime factorization of 108 and see how we can simplify this radical. So 108 is the same thing as, let's see, it's the same thing as 2 times 54, which is the same thing as 2 times 27, which is the same thing as 3 times 9. So we have the square root of 108 is the same thing as the square root of 2 times 2 times, actually, I'm not done. 9 could be factorized to 3 times 3. So it's 2 times 2 times 3 times 3 times 3. And so we have a couple of perfect squares in here. Let me rewrite it a little bit neater. And this is all an exercise in simplifying radicals that you will bump into a lot while doing the Pythagorean theorem, so it doesn't hurt to do it right here. So this is the same thing as, the square root of 2 times 2 times 3 times 3 times the square root of that last 3 right over there. And this is the same thing. And you wouldn't have to do all of this in your head. Well, all of this on paper, you can do it in your head. What is this? 2 times 2 is 4. 4 times 9, this is 36. This is the square root of 36 times the square root of 3. The principal root of 36 is 6. So this simplifies to 6 square roots of 3. So the length of b, you could write as square root of 108, or you could say it's equal to 6 times the square root of 3. This is 12, this is 6, and the square root of 3, well, this is going to be a 1 point something something, so it's going to be a little bit larger than 6.
Okay. This was good. Okay, I hope that video helped. It helps with understanding that PowerPoint, but also later on for other problems that we will face in this course, other topics that we will study in this course. Let's go back to our PowerPoint. Here. Okay, and let's continue. Okay, now in our study, we will talk about some old things that you know, like simple division, quotient, divisor, dividend, remainder, and some new things, fractions, decimals, how to calculate compound taxes, and other stuff. Please know your multiplication table. Try to memorize this. This will speed up your solving mathematical problems. Please, just take your time every day, memorize portion of this multiplication table. Again, we will study some old topics like long divisions, how to divide 34 by 2, and we will divide about the division, multiplication, subtraction, and bringing down, and again, like what we did here. You take 34 by 2, 2 goes to 3 one time, and then you bring 4 down here, so 3 minus 2, 1, you bring that 4 here. 2 goes to 14 7 times, 2 times 7, 14, and the remainder is 0. Okay, we will talk about this later on, but just an example here. Let me repeat this again, because I'm sure some of you are afraid. You're dividing 34 by 2. You put 2 here, you put 34 here. Again, this is like, remember, you have a divisor, you put a number, you're dividing 16 by 3. This part is called quotient, and 3 goes to 16 5 times. 5 times 3, I'm sorry, 5 times 3, 15. You bring it down here, you subtract, remainder of 1. So you go for these numbers like this when you don't know how many times. You may know it from your head that it goes 17 times and you solve the problem. But let's say you don't know. So what you know that 2 goes to 3 only 1 time. So you write 2, you got 34, you write 1 here. 2 times 1 is 2. You bring this 4, and 3 minus 2 is 1. Then you bring this 4 down here, and then you ask yourself, how many times 2 goes into 14? 7 times. 2 times 7, 14. You write 14 here. 14 minus 14 remained as 0. So you've solved you did this long division. So 34 divided by 2 is 17. Okay, again, if you have any question, if you have any answer, please contact me. I hope you go over the syllabus and review the syllabus carefully. Any question that you need, please contact me, email me. Any part of the lessons that you don't understand, email me or call me, contact me. And again, as I said, I either will contact you through email, or I can record a special segment and upload it to Populi for you and everybody else. We are using two books. One, James Nichols, Mathematics is God Silent, and another one, Robert Blitzer, Thinking Mathematically. Please, for the first book, Is God Silent, read the textbook in its entirety according to the dates indicated in syllabus. And same thing with Blitzer. You know, every session we have different chapters that you have to study, and please go over the example, do the exercises for your own self, and that will help you throughout the course. Reading summaries, a minimum of 1 page single space or 2 pages double space. Reading summary will be due each week to the first week of class, and this should correspond to the assigned weekly reading of James Nichols, Mathematics is God Silent. Okay. Please complete the section introducing yourself. Okay, when I'm recording this, we are in Module 1, year 2018, so I have here by midnight of September 9. But because I'm going to use this recording for future, basically by the midnight of the first Sunday of the first week, please complete your assignment, and also complete the introduction too. Maybe I better show this if I can. Yes, hi brother, I'm recording it now. Yeah. Let me, sorry about that. Let me just go and go over the syllabus one thing here. Okay. And again, let's do stop sharing and go to a new, let's go to here. Okay, this is Module 1, 2018. Again, please forgive me if you are taking this course in future and you are not in Module 1, 2018, but it doesn't matter. What I'm going to share applies to whatever session that you will have. Look, basically, for example, Session 1, Module 1, 2018, these are what we are covering, and these are your assignment. They are all due by the Sunday before the midnight of the first week. This class started on September 3rd. The first Sunday was September 9, and we will have that class, all the assignments are due by, for example, at this date, will be due on September 9, 2018. Okay, I hope this is clear. Okay, like for Session 2, you have to do Assignment 3, read Nichols, Chapter 3, do a summary, and also we will have Quiz 1 that must be submitted by September 16, which would be before the midnight of the Sunday of the second week of the class. Okay. All right, let's go back to our PowerPoint again. All right. And yeah, I guess I talked about this, the general math. Please complete that. Again, for the date that I'm talking about would be before September 3rd, 2018. This is an extra credit exam, so it will help your grade. Just take it and don't worry. The purpose of the comprehensive general math test is to help you, for you to understand where you are in mathematics and for me to understand where you are. It gives me an assessment of your mathematical knowledge and ability so that I can focus on those topics that you have weakness. But just again, don't worry about it. Just take it, and it's an extra credit. It's not going to hurt you. It will only help you, and it will help me to understand where you are in mathematics. Again, as I mentioned, I guess I explained this, each week student will have to complete all assignment and quizzes by the Sunday midnight of that week. Okay. We have assignment 4 and 5, known and complete the little known, I'm sorry, it's called the little known facts. Please complete that at the time that is due, and for grading purposes, this will be treated as assignments 4 and 5. You have midterm and final exams. You're required to take this. The first will be offered at the midpoint of the course, week number 4. The second one, the final, on the final day of the class, the week number 7. And here again are how the different assignment quizzes are graded, the value for each different part of the course. Again, if you have any question, please contact me. Now, let's start with inductive reasoning. What is inductive reasoning? Basically, it's a process of reasoning to general conclusion through observation of specific cases. So we look at some specific cases. From those specific cases, we make a general statement. Induction involves observing a pattern, form, observing a pattern and a form, that pattern predicting a conclusion. You observe a pattern by looking at the specific cases, and then you predict a conclusion. For example, imagine an endless row of dominoes. You knocked on the first, which knocks on the second, which knocks on the third, and so on. So by observing specific cases, the case of the first, second, and the third domino, you can make a conclusion for the rest of the material, rest of the what is going to happen. Assuming that the pattern will continue uninterrupted, you conclude that any one domino that you select in the row will eventually fall, even though you may not witness that event. You are making an induction. You are making a prediction, basically, based on observing specific cases. Inductive reasoning is often used by mathematicians and scientists to predict answer to complicated problems. For this reason, inductive reasoning is a part of the scientific method. When a scientist or a mathematician makes a prediction based on a specific observation, it is called a hypothesis or conjecture. Again, a scientist goes into a field, observe specific cases, then based on those cases, makes an induction, predicts a pattern, a form that will continue to happen. So it's basically making a hypothesis or a conjecture of what's going to happen. For example, let's look at the inductive reasoning example. If two even numbers are multiplied together, will the product always be an even number? Okay, solution. We examine the product of several pair of even numbers on the board to see if this pattern happens. So, you can take different numbers. They are all even, 2 and 4, 4 and 6. we multiply 2 times 4, we get 8. We multiply 4 by 6, we get 24. And you can keep doing that. And you will see that, yes, anytime that you have two even number and you multiply them together, you get an even number. So all the products are even numbered. Thus, we can predict from these examples that the product of any two even number is an even number. So you're using inductive reasoning. I hope this is clear. If an odd number, an even number are added, will the sum be an odd or an even number? Okay, then again, let's look at a few examples. On the board, let's look at that. Let me just, in fact, do the stop share and maybe go to the board here. Let's see that. We want to, if we add, going to see if we add even number and a, hope you can see that. Yeah. All right. You can pick a number. This is a odd number 3 plus 4, or odd number 7 plus 2, or odd number 9 plus 6. So 3 examples. You have odd numbers and even numbers. 3 plus 4, 7. 7 plus 2, 9. 9 plus 6, 15. The answer for all of them are odd numbers. But you can do that for many, many other examples, and you will get the same result. So basically, based on that, we conclude that yes, when you add no, where are we? Okay, based on that, we conclude that the sum of all the odd numbers, if you add the sum of an odd number and even numbers are always odd numbers. You might predict the sum of an odd number and even number is always an odd number. So you look at few examples, and based on that, you make a prediction, you make a hypothesis. Okay, so let's go back here. Okay, go back to share screen. Let's go back to our PowerPoint. Okay, so I hope these are clear. A few examples of inductive reasoning. If you have two even number, multiply them together, you always get an even number. So you make a hypothesis, you make a conjecture, your induction reasoning gives you this prediction that if you take any two even number, the answer is always an even number. You take an odd number and add an even number to it, the answer is going to be always an odd number, as we saw. So let's go again through another example. Pick any number that you want. Multiply the number by 6. Add 9 to the product. Divide it by 3. Subtract 3 from the quotient. Then let's see what's going to happen. If we can pick any number, let me just go ahead again. Stop. So that we can go to the board. So let me just remember. So we pick any number that you want. Let's pick 5. For example. Take and then multiply it by 6. It's 30. Okay. Add 9 to the product. 30 plus 9 is 39. Divide the sum by 3. 39 divided by 3, it goes 0, 9, 3 goes 13. So the answer is 13. Okay. And subtract 3 from the quotient. This is the quotient here. This 13 is the quotient. Okay. 13, you subtract 3 from it. The answer is 10. Now, look here. Look here. This is twice of that original number. If you do it for any number, you always get twice the original number. You can repeat this with many, many numbers, as much as you want, but you always get the end result. The end number is twice the original number. So we can hypothesize, we may conjecture that the number you end up with, it will be twice the size of your original number. Okay, let's look at some of the problems in our textbook, pages 3 and 5. Okay. Let's go to your textbook, the one, the Blitzer Thinking Mathematically, pages 3 and 5. Okay. For example, look at example number 2 at the bottom of page 4. It gives you a list of number. For example, identify a pattern in each list of the number. Then use this pattern to find the next number. You have 3, 12, 21, 30, and 39. Um, 3, 12, 21, 3, 12, 21, and 30 and 39. Okay, when you go from 3 to, let's see, what's the difference between these numbers? We want to find a pattern, okay? From 3 to 12, it increased by 9. From 12 to 21, it increased by 9. From 21 to 30, increased by 9. From 30 to 39, it increased by 9. So we can conclude the next number should be 9 more than this one. So it should be 48. You see, you look at the pattern, you see all these numbers are increasing by 9 units. So the next one should be 39 plus 9, which is 48. All right. Let's look at some other examples here. Okay. For example, let's look at, again, same example number 2. B, you have 3, 12, 48, and 48 to 192, and then 768. So if you notice there on number B, example number 2, page 4, the bottom of page 4, from 3 to 12, you have increased by 4. From 12 to 48, you multiplied by 4. So, you know, it's all multiplying the numbers by 4. That's the reason you get to 768. You just multiply it by 4, you get the next answer. Let's look at the next answer, which would be 3072. Let's look at, for example, number C. You have 3, 4, 6, 9, 13, 18. Oh, that's very interesting. Let's do this one on the board. Yeah, it's fun. You have 3, 4, 6, 3, 4, 6, 9, 13, 18. 9, 13, and 18. So from 3 to 4, we are increased by 1. From 4 to 6, we are increased by 2. From 6 to 9, we are increased by 3. From 9 to 13, we are increased by 4. From 13 to 18, we are increased by 5. So if you look at the increase for each one of them, the first to the second is 1. The second to the third, 2. Then 3, 4, 5. So if I'm going from 18 to the next number, the increase should be by 6. So the next number should be 24. Again, this is inductive reasoning. I'm looking at these specific cases and I'm making a prediction. I'm making a hypothesis regarding the future. Okay? All right. Let's move on. I think we can just go back. Okay, let's go back to our PowerPoint. No, not this one. Okay, we did that. Now we come to deductive reasoning. Deductive reasoning is just a reverse of the inductive reasoning. The process of the deductive reasoning, it's a process of reasoning to a specific conclusion from a general statement. See, in the inductive reasoning, you look at specific cases and then you made a general statement. Now, in a deductive reasoning, you have a general statement. From that, you make prediction regarding a specific situation. And mathematicians, scientists use deductive reasoning to prove whether a hypothesis is true or false. So, you see, what's the connection between inductive reasoning and deductive reasoning? In inductive reasoning, we look at specific cases, we make a general statement. But then, in order to make sure that's true, that is a valid hypothesis or conjecture, we use deductive reasoning. In other words, we take that general statement and apply it to some other specific cases to see whether it will follow the same pattern that we were predicting. A conclusion that is proved to be true by deductive reasoning, then it's called a theorem. A theorem. Okay? To use deductive reasoning, we begin with general case rather than specific cases. For example, let's use the same example where a specific case were used, but not using the letter N. Remember that number that I said, pick any number, then do all kind of things to it. You will end up having the value at the end would be twice the value in the beginning. Now let's make a general statement. Instead of any number, we use N to represent any number. Okay. Where are we? Okay, now on page 7 and 8. Now before, okay, this maybe this slide is not the best position. Let me go here. So you pick any number, multiply it by 6, add 9, you pick any number, N. You multiply it by 6, you get 6N. 6N means 6 times N. You add 9 to it, then you divide the product, the result, by 3 and subtract 3 from the quotient. So we picked any number N, multiply by 6, add 9, then we just divided the whole thing by 3. 6N divided plus 9 divided by 3 will become 6N divided by 9 will become 6N divided by 3 will become 2N. 9 divided by 3 will become 3. Then you subtract 3 from the result, from the quotient, you end up having 2N. So this proves that if you do these mathematical operation, the final number would be twice the original number. Again, maybe I think you guys may have some problem with this part, 6N plus 9 divided by 3. Let me do that for you on the board. So I need to shift again. Okay. And maybe bring this closer. Okay. So we pick any number, N. Okay. Let me just look at what did I say myself. You multiply it by 6, it becomes 6N. You add 9 to it, plus 9. Then you divide the whole things by 3. Now, what does this mean? 6N plus 9 divided by 3 is the same as 6N divided by 3 plus 9 divided by 3. Okay, these two are the same. Then, because they have one common denominator, you can write this separately and this part separate. Then you have 6N divided by 3 is cancel. 6 divided by 3 is 2. You get 2N. 9 divided by 3 is 3. So okay, this is what you get. Then say subtract from the quotient minus 3. So the end result is 2N. So 2N is always twice the original value. Remember, in the example that you did before, we took different numbers and we came with twice the number. We picked 5, we ended up with 10. But here is a general statement. This is deductive reasoning. The other one was the inductive reasoning. What this deductive reasoning proves, the hypothesis, the prediction of that inductive reasoning, now this becomes a theory. Okay? Because it was proved to be correct. All right. Let's go to share screen. Okay, let's look at pages 7 and 8. Okay, let's look at pages 7 and 8 of our textbook, some of the example in our textbook. For example, look at example number 4 on page 7. You have those picture of circle and a square, circle and a square. If you follow that pattern, what should be the next shape? Should be a square. Okay, that's one part. But then look at those dots. Look at how they are moving. First of all, we see that all the shapes have 4 different segments, okay? And the dots, look at for example, look at the first square. The single dot is on the right-hand side. But when you go to the square one, that single dot has moved to the next top segment. And then when you go back to the second square, it moved to the third segment. It moved to the left side of the figure. Then you come to the second square, that single dot has moved down at the bottom of the square. So the next shape, which has to be a square, must have that single dot again must move one segment up. In other words, let me show you. In other words, so we have, sure, put the picture here. So we have circle, square, circle, square. So the next shape should be circle. Right. So the next one should be a circle. And again, they all have 4 parts. Now in the previous figure, in the previous shape, which was a square, that single dot was here, okay? The 2 dots were here, the 3 dots were here. So when you move to this one, this goes 1 up, and the 2 goes here, and the 3 goes here. So you can see the pattern, it's repeating itself from circle to a square, circle to a square. Therefore, the next one is a circle, and we all see these dots are moving from, kind of counterclockwise in each figure. Look at, for example, the checkpoint number 4 on page 7. In checkpoint number 4, we have a square, then with this connection here. Then we have a triangle with 2 connections, 2 legs, and then we have a square with 3, and the 4th one, again, a triangle with 1. Okay, so we go from square to triangle, square to triangle. So the next figure that we don't know must be a square. Okay, and notice these legs. 1, 2, 3, 1. I predict the second one should be like this. 2. This pattern is repeating itself. 1, 2, 3, 1, 2. So this is the next shape. Okay. I'm looking at, this is actually an example of a inductive reasoning. I'm looking at the pattern and I'm predicting the future. But let's go, for example, to page 8, example number 5. This is similar to what we did, actually. It says, consider the following procedure. Select a number, 4, multiply it by 6, you get 24, add 8 to it, you get 32, and divide this by sum by 2, you get 16, and then subtract 4 from it, you get 12. And we keep repeating this, and if you do that, you look at number at the bottom, table number 1, at the bottom of page 8, they pick number 4, 7, 11, and 100. Each time when they did that procedure, they ended up with a final number which is 3 times the original one. So then they can come, so this is an inductive reason. They say you pick a number, you do this operation, you end up with a number which is 3 times the original one. Now we want to use deductive reasoning to prove that whether this hypothesis is true or not for all numbers. So let's do this. Pick any number n. Okay, multiplied by 6, it becomes 6n. Add 8 to it, it becomes 6n plus 8. Then it says divide this by 2. Okay, remember, I can write this by itself, and I can write this by itself. 6n, this is same as 6n divided by 2 plus 8 divided by 2. 6 divided by 2 becomes 3n, plus 8 divided by 2 is 4. So this is my final answer. Then it says subtract minus 4 from it. So I got 3n plus 4 and minus 4, which is equal, these two cancel, we end up with 3n. So this was the original, this is the final, 3n. So you get 3 times the original number. This is deductive reasoning, which proves that former inductive reasoning that you see on table 1.1 at the bottom of page 8. Okay? All right. Let's go to our PowerPoint. Okay. We did that. In our first example, you may have conjectured using a specific example and deductive reasoning that the result would be twice the original number, even in our own example in our PowerPoint, not the textbook. But in the last example, we proved using deductive reasoning that the result will always be twice the original number. Okay, let me stop this. One moment. There's a problem. I have to stop this.